Well, I'm excited to give you a talk on this paper that I wrote while working on my dissertation at UCLA with these lovely, wonderful collaborators. Is it down is next? Yeah, so what we do a lot of work on is tabular synthetic data. And so the idea with tabular synthetic data is, say you have some like real table of continuous and categorical data, like anything that's going to fit into like a database or a CSV file or a spreadsheet. A lot of people have been doing work where you can train a generative model to learn the joint distribution of that table or of that sample, and to use that generative model to generate synthetic samples. And the idea with this is that the synthetic data is going to well model the joint distribution of your training data, and therefore, like if you run a query or a statistical model on the synthetic data, like a linear regression or something, it'll be very similar to that of what you would get if you ran it on the real data. And so people have been working for about 5 or 6 years now on this kind of regime, because the idea is that you can have some sort of privacy benefit by just sharing the synthetic data rather than like the protected hospital records or whatever that make up your real data. And so lately, people have been using LLMs as like state-of-the-art tabular generators and making claims about the privacy of these data. And so there's 2 regimes people have been using for LLM-based tabular generation. There is in-context learning and supervised fine-tuning. In both cases, the general vibe is that you have some original tabular data set, like, again, something that like you could fit a linear regression on. You encode it into some text, and then you throw that into your language model, either in like the context window, and then sample out of that in the in-context learning case, or for supervised fine-tuning, you SFT your model on that. And usually that's like a smaller LLM. And so kind of the position of this paper is that LLMs generate data differently than like prior ways folks have been using to generate this synthetic data. For a long time, folks have used like graphical models and GANs and VAEs and diffusion models, which model like this joint distribution over a whole feature vector at once. LLMs like fundamentally don't do that. They encode rows as strings, you generate token by token, and then you just like string parse whatever it comes back into like your CSV format. And so like fundamentally, the atomic unit of an LLM is a token, whereas like all other models folks have used for this operate over like the feature space or like the Cartesian space of these tabular data. And so what we're interested in is, do LLM tabular generators leak privacy through their string representations in this kind of autoregressive token by token regime in ways that like traditional traditional adversarial attacks for these like feature vector-based models don't. And so to give you some like intuition for what's going to happen here, imagine we have this record in our training data set that we wish to attack, and our model has generated this like synthetic row. By just looking at the numbers, you can tell like this vector is like very far away in the Cartesian space, or like from a Euclidean distance perspective or something, than the synthetic record. In this case, like by 10,000 units. What we observe though in this paper is that like your LLM will generate like strings that like are far away in like the feature space distance, but are very close in terms of a string similarity perspective. So like instead of 97540, it'll generate stuff like 107,540. And so like the idea is like, well, can we potentially like exploit this for an attack? And so we do a very brain dead, simple, easy operation where we just assume under like the most conservative, like no box threat model possible, where the adversary only has like the synthetic data that's released. We don't assume any model access, training, reference data, nothing. We simply compute like in a membership inference attack for a candidate record X star, which is either in the training data or not. just compute the minimum Levenshtein distance between your candidate record and the nearest neighbor in the synthetic data record. So, and the idea for this is that Levenshtein edit distance is a measure of string similarity from ye olde NLP ways, where the distance between 120.1 and 221.1, I only need to change one character in that string to make both strings equivalent. So like the distance is 1. If I had 2 strings that were very different, the distance is greater. And so we basically just run this attack on a bunch of different LLMs on a bunch of different data sets and find some pretty bad results. So this is for the ICL case. We found that over a pretty big benchmark, in like the top 20 most egregious runs, many of these models like catastrophically leaked the membership of the training data. So like if AUC equals 1 is a perfect classifier, oftentimes we would see like this very simple string similarity attack is like a perfect classifier. And indeed, we find that like on some data sets, like the state-of-the-art like in-context learning approach has like just measuring like how like the edit distance between 2 strings is a perfect classifier of like the membership of the training data. And this also is compared to like attacks that target the feature space or like the Cartesian space of these data that don't find like this sort of privacy leakage occurring. This gets replicated in the supervised fine-tuning, although it's to a lesser extent. The main results from this are that like high fidelity, like the greater and higher fidelity your LLM generates the synthetic data, the more leakage there usually is. And additionally, this attack doesn't work on things that are not LLMs. So we compare this with like a variational autoencoder and a GAN-based method, and like this character level string similarity thing is completely random. There's like no advantage you can find here. And so some additional things, we run a bunch of other experiments we can talk about at the poster, but there are a variety of things that like contribute to greater leakage. If you increase the amount of synthetic data you are generating, you have like way more leakage as that goes up, because your LLM has like more opportunities to just create stuff that is totally memorized. And additionally, the more like information and like the longer the digits and stuff that you like have in your training data, usually the greater danger that you have with leaking these things, because it memorizes these like different motifs in these numeric sequences and categorical sequences. So the kind of takeaway from this, from like an interpretability AI perspective, is like a lot of these papers will claim like, oh, my LLM learns like the joint distribution of the training data from like a statistics perspective. But this looks way more like a stochastic retrieval process, where it just like retrieves some rows and like throws some noise into it, and it like it says it's good according to our metrics. So we're running a little low on time. We propose a big defense for this. I won't go through like the algorithm, but the whole idea is that we propose a defense where at sampling time, so this will work on any LLM, it integrates with Hugging Face and VLLM. So at sample time, when your LLM produces like its logit distribution that it then wants to sample from, throw like a tiny bit of noise into that thing. And by doing that, it throws off the sampling trajectory of like it memorizing these patterns of categorical data and like numeric sequences. And so we show that by like doing this algorithm, you can decrease the privacy leakage from the Levenshtein attack from like in the high 60s and control it down to like basically random, while having like no cost in the fidelity of your final synthetic data. Because you can break up the string level character patterns at this like character representation level without destroying any of the fidelity or a little bit of utility in like the implied Cartesian space of that data, which is very cool. So the summary of this is, don't use these models. They are not pets. This like work kind of shows that like these tabular generators that are based on LLMs because they like represent data differently than all of the other ones, introduce like a new and independent string space attack that can have like leakage that's very independent of stuff that happens in your Cartesian space. This Levenshtein attack is able to like find like catastrophic privacy leakage fairly trivially under like the most conservative threat model we can like possibly imagine. I mean, I guess you could just, well, I won't go there, but I guess you could say it has less synthetic data or something. And then finally, we propose a defense that is like fairly able to deal with this attack. And this defense you can throw into whatever model you're working on, assuming you're sampling out of like, you're using like a Hugging Face or VLM API. So that is our talk. If you want to ask me more about this or hear my thoughts on tabular data more generally, you can come hang out at the poster session. Thank you so much.